All right, so we're going to take a look at some titration problems here. And in this first example, we're going to compare the titration of HCl, which is a strong acid, versus HF, which is a weak acid. They are both monoprotic, meaning they both have just one hydrogen, and they have the same concentration and the same volume. So we want to think about the similarities and differences for how these titration curves are going to look. So the first question is, if we titrate these samples with 0.2 molar potassium hydroxide, how much base will it take to reach the equivalence point? Well, first of all, we need to look at the chemical equation here. So HCl and KOH, it's going to make KCl and water. And then HF and KOH is going to make KF and water. So what we notice here in both cases is they react in a 1-to-1 ratio. And that's what we'll find of any monoprotic acid. It'll react with a base such as potassium hydroxide in like a 1-to-1 ratio, one hydroxide for every one hydrogen. So, okay, that's one thing to know. Now let's think about how much acid we have to begin with. So if we can figure out the moles of acid by taking the molarity of the acid times the volume of the acid. So the molarity is 0.1, the volume is 0.025 liters. So we have 0.0025 moles of acid, and that's true in both beakers. So you've got the amount of acid in beaker 1 is the same as the amount of acid in beaker 2. And we know they react in 1-to-1 ratio, so therefore you need equal amounts of base. So since it's a 1-to-1 ratio, the moles of acid is going to equal moles of base. So that means in both cases you need, 0.0025 moles of KOH to neutralize your sample. And we know the KOH has a molarity of 0.2 moles per every 1 liter. That's one way we can write molarity there. So you get 0.0025 divided by 0.2 times 1,000, and that gives you, I'll write in the times 1,000, that gives you 12.5 milliliters. So a key thing is that for both of these samples, even though one's a strong acid and one's a weak acid, since they have the same volume and same molarity, it's going to take the same amount of base to reach the equivalence point. So in both cases, it takes 12.5 milliliters. And I showed how you can do a calculation here. Another thing you can do if this is like a multiple choice question and you're just doing some quick mental math is you could say, well, my 25 mil sample is 0.1 molar, and then my base is twice as concentrated. So I'm going to need half as much base to neutralize my acid. So notice how 12.5 is half of 25. So that's another thing you can do with some kind of mental math there. Okay, so the amount of base needed to reach equivalence is the same. Well, let's look at the pH at equivalence. So to find the pH at equivalence, we want to consider what the net ionic equation is. So for the strong acid, so this is like the HCl titration. The net ionic equation is H plus OH makes water. So at equivalence, it is going to be neutral. So this one's going to be neutral, pH equals 7 at equivalence. For the weak acid, the net ionic equation looks like this. Because the weak acid does not totally dissociate. So what you're left with here is the conjugate base here. So the pH is going to be greater than 7 at equivalence. And the reason why is because F minus is a weak base. All right, who's got the lower initial pH? So you've got, what we're comparing here is 0.1 molar HCl versus 0.1 molar HF. HCl is a strong acid, so it's going to completely dissociate and form H plus ions. So if you have 0.1 molar HCl, that means you also have 0.1 molar H plus ions. And so that's going to be a pretty low pH. All right, and then this one over here, the weak acid does not completely dissociate, so it's going to make less, you're going to make fewer H plus ions over here. So this one's going to have a lower initial pH. So in this case, it would have like a pH of 1. And then this one, we don't know exactly what the pH is if we don't know the K value, but it's going to be less. So it's going to dissociate less, it'll make fewer H+ ions. So let's do a quick sketch of the titration curve. So if we were plotting these out, let's say this is the titration of HCl, this is the titration of HF. If you look at let's make this 7 here. HCl is going to start with a lower pH. It's going to start down here at the pH of 1. HF is going to start somewhere higher. We don't know where exactly. They're both going to reach the equivalence point at 12.5 milliliters of base added. But the strong acid curve is going to look a little bit like this and be very dramatic. And we should find that the pH is equal to 7 at equivalence. The HF is going to look more like this. It's going to kind of go up a little bit, and then it's going to go like that. So it's going to be a little bit of a shorter vertical region. And if you look at the pH at equivalence here, it's going to be somewhere greater than 7. So we can see the similarities and the differences in these two curves here, your strong acid versus your weak acid. Okay, let's look at another graph here. The question here is, what is it? Is it a strong or weak acid? One way to spot it is to look at the equivalence point and see what the pH is. So that's the equivalence point. It's kind of like the halfway of this vertical region here. And I'm going to estimate the pH is around 9 at equivalence. So that tells me that it is a weak acid because weak acids have a high pH at equivalence because you will form the conjugate base. So that's because the product is going to be a weak base. And as a reminder, this is what that net ionic equation looks like. You got a weak acid, you're adding hydroxide, and this is what I'm talking about here when I say the product is the weak base. This A- right here, that's what's causing the solution to be basic at equivalence. If it were a strong acid, we'd be making water, and we'd expect it to be neutral at equivalence. Okay, so pH at equivalence is 9. I already answered that one. Boom. And when we're titrating a weak acid, throughout the course of this titration, like initially you start out with pure weak acid. At the equivalence point, you have pure weak base. That's why the pH is high. And when you're somewhere here in the middle, you're going to have a combination of a weak acid and its conjugate base. You're actually going to have a buffer. And if you stop at exactly halfway to the equivalence point, which I'm going to need to erase this here for a moment. Okay, so it looks like my equivalence point is happening at around 30 milliliters. So I'm going to say the half equivalence point is right here around 15 milliliters. At the half equivalence point, so like halfway to equivalence, the pH is equal to the pKa of the acid that you are titrating. So I'm going to estimate that maybe the pKa is around like 4.5. Or maybe you said 5. We're estimating, so somewhere around there, like 4.5 to 5, maybe. It seems to be your pKa. And your pKa is the negative log of the Ka. So the Ka is 10 to the minus pKa. So that means the Ka of this acid would be 10 to the negative 4.5, which kind of confirms what we were thinking about being a weak acid. Okay, this graph, is it a weak or strong base? So again, I can use my pH at equivalence here to help me figure this out. I'm going to say the pH looks like it's around 6 at equivalence. And so that tells me that I am titrating a weak base. And a reminder, this is that reaction that's happening for weak bases. So your weak base combines with your strong acid to form the conjugate acid. So the product of this titration reaction is a weak acid. So that's why your pH is around 6 at the equivalence point. And I guess I kind of already answered this question. All right. So that's why the pH is less than 7 at equivalence, because you form the conjugate acid there. And if you look at these ones, we've got two titration curves. They're both weak bases. And which solution of base is more concentrated? So let's look at the equivalence point here. So it looks like this base took about, I don't know, I'm going to estimate maybe like 38 milliliters of acid whoops, actually these are acids. I said weak bases. These are actually both weak acids. Whoopsies. This one took about 38 mils of base to neutralize, whereas this one only maybe took, it looks like only took about 30 milliliters of base to neutralize. So since this solution took more base to neutralize, that means this one is more concentrated. So to figure out the concentration, you're looking at like how much base was needed to neutralize the sample. Let's look at the KB though. So if we look at the KB, and again, this should say, I just realized that I goofed here on this one. Sorry. This should say acid and Ka. My apologies. I have this mislabeled here. So these are both acids here. And you estimate the Ka by looking at around the half equivalence point. So this one has a pKa of around, I'm going to say maybe 7.5 is my estimate. And then this one, I'm going to say it has a pKa of around like 5.5. So I'm going to estimate there. So if I were to find the Ka, would be 10 to the minus pKa. So this is around 10 to the minus 7-ish, and this would be around 10 to the minus 5-ish. So that tells me that this is the stronger acid. It's going to have a larger Ka. Something else you'll notice about it is it has like a taller vertical region. That's another indication that this acid is stronger than this one over here. We should also find that it has a lower pH at equivalence. So this one, the pH at equivalence is around 9. This one, the pH at equivalence is around 10. And then what that tells us is the stronger the acid, the weaker the conjugate base. So that's why this acid, which is a stronger acid, has a lower pH at equivalence. The weaker acid has a stronger conjugate base, so it's going to have a higher pH at equivalence. So there's a couple other tidbits I'm adding onto there. All right, so let's look at this one right here. This is a calculation one here. So we've got a monoprotic acid. So what that means, monoprotic means just got one hydrogen. So let's write this out and figure out the stoichiometry here. So it is going to be a 1-to-1 mole ratio when you've got a monoprotic acid there. We need one hydroxide for every one hydrogen. And it's titrated with 0.112 molar NaOH. And if we take a look at this graph, I'm going to estimate that it took around 25 milliliters of base. So it took around 25 milliliters of 0.112 molar NaOH for us to reach the equivalence point of this reaction. Remember, the equivalence point means all the reactants have gotten used up there. So I'm going to plug that in my calculator. So if I want to find out how many moles of base that is, I take my molarity times my liters, and that's going to give me moles of base. So that means I got 0.0028 moles of NaOH. And since it's monoprotic, it's going to react in a 1-to-1 ratio with sodium hydroxide. So what that means is I also have, if it took 0.0028 moles of sodium hydroxide to reach equivalence, that means there must have been 0.0028 moles of my acid in the sample. Again, why? Because it's a 1-to-1 ratio. And if you're doing this on a test, you want to, specify somewhere that you're acknowledging this mole ratio, or you can show it. You can show it out mathematically like this as well. But don't forget to acknowledge the mole ratio somewhere or include it in your calculation. Okay, so last question though is you want to find the molar mass. The molar mass is the grams per mole. So the grams is 0.229 and the moles is 0.0028. So we divide that 0.229 divided by 0.0028, and you end up with 81. Let's see, how many sig figs should we have? I think we should have, let's say we're going to have 3 sig figs. Okay. 81.8 grams per mole. That's the molar mass. Other question also asked me for the pKa. So I'm going to say the pKa is around 3. Okay, and I estimate that from the half equivalence point. All right, hope that helps.